Hey physics nerds, Mr. McLeod here. I want to talk to you today about, or as you notice, it's the same day, same clothes as our previous video, but I really want to do is get a bunch of these little short videos out of the way. That way, when I'm giving you the work for the next week or so, we can spend our time just hashing through the math problems and the drawing and the process of physics, and you have a resource you can turn to that just has all the basic information. So we're going to use our time as wisely as we can. All right, so 3 things today: coordinate systems, distance, and displacement. We're going to talk about those three things, and then I'm going to sort of cut the video and start another video on trig. They all kind of fit together really nicely, but I don't want this to be a super long video. I want you guys to have little chunks you can watch it through. So first things first, coordinate systems. Okay. You guys are used to using coordinate systems in math, even if they don't call them coordinate systems. And the way the coordinate system looks is completely based on how many dimensions you're working in, and also your perspective. All right, let's start from scratch. We'll start here. I'm going to put a 0 here. I'm going to draw a line, and we'll write, 10 over here. You guys will recognize this is the number line, right? And we'll go the opposite direction and we'll write -10. Sweet. All right, we have a number line. If you lived on a number line, if you lived in a universe where you could only go in one direction or another, you cannot go in or out or forward, and you basically only had 2 directions of travel, but really just one line of travel, that would be a one-dimensional line. In physics, we like to start with one-dimensional physics because it takes a lot of the complications out of it. Eventually, we'll move into 2-dimensional physics, and 3-dimensional physics is actually far beyond what you'd even learn in an AP physics class. 3-dimensional physics gets really, really complex because you have so many formulas, you might need matrices, things like that. Keep things simple, one dimension. Okay, so here we are. Let's say we're Bob, Bill, Juanita, what do we want to call this stick person here? This genderless stick person. Our stick person is going to walk in this direction. And let's say he walks in this direction, or she, for 5 meters. Okay, walks 5 meters, boom, and then decides to turn around and walk back 7 meters. That's not so bad. So he goes back 7, which would put us at -2. Now, this is what I want to ask yourself. Does it matter that this direction is positive and this direction is negative? Does it matter at all if I said, Susan here, change the name constantly, walks from here to here and walks -5 meters, and then walks from here to here a positive 7 meters? Well, not really. Well, we're still going to end up in the same spot, but our numbers are going to be all different. And so in physics, and your perspective matters a lot. It isn't always necessarily beneficial to say that to the right is positive and the left is negative. It is in normal mathematics, and for now you want to keep it that way, but there might be some situations where you want to flip these ideas around. Let me show you an example. I'm going to walk across the floor here. I'm going to pick you guys up here. Try to rotate this without it getting mad at me. All right, and I'm going to look at the floor so you guys can sort of see. I'm walking along a nice little number line here. My gimbal's having a little bit of trouble here. There we go. There we go. Now it works. Okay, zoom in a little bit too while we're at it. All right. So if I walk forward 2 meters. So if you notice, I have 2 meter sticks on the ground behind me. I walk forward 2 meters, and then I decide to walk, turn around and walk back 3 meters. You could say that I am -1 for my starting point because we did 2 minus 3. But a problem with that is, what does -1 mean? Does that mean I physically went a negative distance? Or does it just, I mean, we know the answer. It's literally just a naming convention. We like to sit there and keep track of distances by keeping them having opposites. But in all reality, all distance traveled is positive. We're never going to go back in time and reverse something that we did. We may go back over the path we took, but we're not going to reverse it. So if I were to add up everywhere I walked, so let's say I start here, see my foot here on the floor, and I start walking forward, walk 2 meters, and then let's say I walk to the left a meter, and then I walk to the right 3 meters, and then I walk to the left another 3 meters. Okay, we could say that the length of my path is a total of 3, 4, 5, 6, 7, 8. I think I added one too many earlier on. 8 meters. Length of my path is 8 meters. And then if I walk back another 3 meters to this corner over here, that does not mean I lost 3 meters on my total distance. If you looked at my watch and you got my step count for today, it would not show that I lost things because I walked over the distance. It's going to be 8 plus 3. It'll be at 11 meters. And so when we're talking about distance, we're talking about the total length of the path that we walked or the path that we went. Let me write that down. This may not be something you're familiar with. When you use the word distance, you usually use the word distance to just mean how far did you go. And there is a difference between how far you are from where you started and how far you went. I'm going to erase this real quick. Sorry, Linda. And distance, okay, which we typically give it the variable x and sometimes y if we're dealing with 2 dimensions. Distance means, use a different color here because that's coming out a little dim. Distance means total length. I'll write it in a full sentence here. The total length of a path. Okay, so basically, if we add up all the parts of our path, forward, backwards, left, right, distance is always going to be a positive number. All right, now, you may hear me use the word distance this year, and I don't actually mean distance. That's a common issue. In English, we use the word distance, but what we really mean most of the time when we're using the word distance in English is we really mean displacement. Displacement is the I don't want to use the word distance to describe displacement. It's hard to do. But basically, I want to know how far it is between my starting and my ending point. Even if I start in one spot, I walk a certain path, I walk back a little bit, I walk this way a little bit, and then I walk back over here, displacement is just how far where I was starting to where I ended up. Distance is the length of the entire path taken. So if I would literally be adding up everything as long as I go. Okay, we also use x and y for this, but more than likely, just about everything we do in physics involves displacement and not distance. And oftentimes, instead of saying x or y, we'll use this triangle here, which means change in x, okay? Or change in y, or change in whatever we're doing. But when it comes to displacement, x and y are usually the ones we stop with, because we like to stop in 2 dimensions, and we'll talk about that in a minute. Remember, change in x and change in y literally just means our final position minus our initial position for x, right? X final minus x initial. Now, you might remember this is known as the distance formula, okay? In your mind, you might think of it instead as being the displacement formula. But basically, if I start here on the path, I know you can't see my feet right now because I'd be on the counter. and I walk over here to the end of the second meter stick, I know if I took where I ended up, which is 2, if this was an imaginary number line, if I ended up at 2, and I subtracted that from where I started, which was 0, I will get the total displacement I traveled along the path, displacement. So in this example, I'd have a displacement of 2. All right, this is very, very, very simple in one dimension, right? I could go back and forth all day, but all we care about is where we ended up. If I was a particle, let's say we're taking chemistry right now, or we're doing particle physics, which I may talk about throughout the year, and you have particles whizzing all over the place. But when I take my measurement can only pick up where the particle started at one point and ended at another. And so a lot of times in physics, we like to skip the path. We call this superposition. I'll talk more about what that physically means later on this year. But we like to skip the path, and we just like to look at where we started and where we ended. Okay? And that often tells us a lot of information. Does that mean everything in between isn't important? No, it can be important. But we can't know every moment in between every other moment. Okay, you can continually break down moments of time indefinitely as far as we know. And so that's why we look at 2 points, starting and ending points. Okay, this is where we find the average. If you guys are taking calculus, we do better at this. we do get infinitely small in our things using tricks in calculus, which is why Isaac Newton invented calculus. But for this class, we use algebra. We use the distance between 2 points, and we don't care what happened in between those 2 points as much. Such as if I were to graph what I did here, and here in physics also, just so you know, man, these markers just aren't doing it for me today. What is going on? All right, if I were to graph, and I were to say this was our displacement, I know you hate seeing that X on the y-axis, but that's because time always goes on the x-axis. And the reason time always goes on the x-axis, if you know the rules of functions and stuff like that, you never have a function that kind of rolls back on itself. Well, that's really useful for time because you're never going to lose time. We're never going to time travel in physics to the past. I mean, physics, things time travel to the future all the time, but things never time travel to the past. We're never going to say how much negative time went by. It doesn't make any sense. So we put time in the x-axis. We can go up and down the y-axis all we want, but on the x-axis, we're always going from left to right. Time's always ticking on no matter what we do. Even if an object's stationary, time is still ticking on. So, let's say on our distance time graph here, we know I ended up at 2 meters at some point. And I'll just put 1 and 0 here. It's not a very well drawn graph. You can see the spacing's a little off. That's fine. It's for educational purposes only. As it is. Let me rotate just a little bit, just in case you can't see some of this. All right. So, and then down here we'll say 1, 2, 3, 4, 5, 6, 7. All right, cool. Let's do this. I started here. And let's say I don't move for 3 seconds. 1 Mississippi, 2 Mississippi, 3 Mississippi. And then I start walking. And I get to the stopping point. And then I turn around. And I return back to my starting point. Okay, let's say that turnaround time, I spent 1 second turning around. So, if I were to graph that, use a different color so you can see it against here, it would look like this. I stood still for 3 seconds because my displacement was 0. I was 0 away from the starting point. Then I walked the 2 meters. I'm going to say it took me about, let's say it takes about 2 seconds to walk 2 meters. And so at this point, I'm literally going to connect the dots that way. I'm going to say it took 1 second of me turning around, and then I need another couple points here, 8, 9, let's say. And then let's say it takes me 3 seconds to return to the starting point. And there we go. We get a graph of our displacement versus time, and this is known as a distance time graph. I know I'm using the word distance, but I really mean displacement. Distance time graph. All right, now you can learn a lot from this. Like if I were to take the slope of this line, the rise over the run between these 2 points, I'd probably get an average velocity. I'd get a speed of how fast I was moving. How long did it take me to go this far? And vice versa for the other end. Okay, we're not going to worry about that quite yet. Those are things we're going to get into, and we're going to move into more complex things. What I want you to notice, though, is did I move at the exact same speed the whole time I was walking over there? No, probably not. I think I looked back at the camera, I took my time. You guys can rewind and look at it. But the thing that's really important here is we don't care about that time. I never specified that I was going to be taking any data points during that time. I took a data point here, a data point here, a data point here, here, and here. Does that mean I couldn't go back on the video and watch it and try to track these individually? Yeah, I can. But even then, we might say, well, what about that half a second between there and there? I can't really tell in the video if his foot was moving forward or pausing. So there's eventually a point where we can't get enough information. And that's true for every experiment in the history of science of physics. There is no such thing as a perfect measurement. Every measurement will have error. Every measurement will have uncertainty. I think we talked about this a little bit in the last video, where I said physics is that a measurement is useless without its uncertainty. So if I were to if this was a professional paper, or I was trying to put this out there, I might say something along the lines of points in time were only recorded whenever there was a change in motion. So I might have said, well, if I was sitting still, I wasn't really paying attention. If I was walking forward, I didn't really check my points until I got to the end. I would make that statement, and that would kind of give people an idea of how accurate this is. Not very accurate, as you guys know. You watched me do it. But this is kind of the way that we graph things, right? And we learn a lot from this. I know personally, I could look at this and I could say, okay, this is a straight line. There's no curve. If it was curved, that means I was changing speed continually. A straight line implies constant speed or constant velocity. We'll talk more about the difference between those later. But straight and curved lines tells us a lot about what's going on in physics as well. And so a single graph of data can be used multiple times to tell you all sorts of things about a situation. All right, now I'm going to leave this alone because we can go down this rabbit hole later in a lot more detail. I want to now talk about two-dimensional coordinates. So I walked back and forth a couple times. I taught you some things about basic coordinate systems, but let's talk about two dimensions. Now, I just drew a two-dimensional graph, I know, but those two dimensions were time and one axis, an x-axis. We don't want to think of time as a dimension at this point in physics. We don't want to be plotting time with x and with y. It becomes a major pain. So what we want to do is eventually we want to collapse our x and y's into a single distance. That means we have to deal with a little bit of trig, right? We got to go, oh, I kind of went in that direction. That's this much x, that much y. You guys might get the idea that we're going to have to use a little Pythagorean theorem in there to figure out a single number for displacement. We don't want a big mess of data like that. So now I'm going to draw a graph that represents the floor here in the classroom. And this will hopefully be helpful for you. Okay, now I could draw a square, but I'm going to use a graph and actually, I might need some negative space here. Let's go this way, and let's go this way. I don't know. Now, I want to tell you this because this is something I want you to tell yourself when you do some of these assignments. I am deciding that up is this way. I am deciding that right is this way, which I guess is, I don't know, sort of east facing. And I'm deciding that left is that way, and down is towards you guys on the camera here. Okay, I'm also going to decide, now, could I rotate this and split it any way I want? Sure. It's up to you how you want to draw your coordinate system. That could be dangerous because once you pick it, you can never change it. You got to keep using it for an entire problem or an entire physics experiment you're doing or lab. But I'm deciding right now also that if I'm going north, it's positive. And if I go south, it's negative. And if I go west, it's negative. And if I'm going east, it's positive. Now, Why did I pick this? Well, it makes me more comfortable because I'm used to positive and negatives being this way on a graph. Is it a graph? No, it's a map, really. But it's going to look and act just like a graph. Like I said, when you pick your coordinate systems, it's up to you, the orientation. This could get you in trouble though, just using this one all the time. Because eventually we're gonna be dealing with things on ramps that are tilted, and we're gonna actually wanna tilt our entire coordinate system to sort of line up with the object that's sliding down a ramp. And that causes some confusion. And actually it's not even tilted this way, it's actually completely 90-degree tilted. But don't worry about that until much later. Just keep in mind, you decide your coordinate system, but once you decide it, you stick with it, okay? And you gotta pick what's positive and negative. And you gotta remember that things that go in the opposite directions are negative. All right, so let's go on our walk again. But this time I'm gonna add in both dimensions for it. Okay, pointing downwards. Okay, and actually, you know what I might do? No, that's fine. I was gonna rotate the camera, but I'm like, that'll look terrible on YouTube, actually. All right, so I'm gonna look down, hopefully enough so you guys can see my feet. Okay, all right, and I'm gonna start here, and I'm gonna go, okay, 1 meter, 2 meters, that way. All right, so I'm gonna write it down real fast on the board. Okay, that I went, oh, by the way, so you guys see where I'm writing this? I have, oh, by the way, also, I'm going to be calling the horizontal axis. That pin is dead now. Well, these things are not lasting. I'm going to be calling the east-west the x-axis and the north-south the y-axis. Once again, I'm just doing that because it's easier for me to look at and think about, right? That's what you want to do. You want to be comfortable with your coordinate system. And you also want to make sure it's logical, because, you know, it's physics, right? It's got to be logical. All right. All right. I'll turn off it's trying to track the board here. There we go. All right, back to the floor. So I'm going to write on the board if something's an x coordinate or it's a y coordinate. Actually, you know what I'll do? I'll draw it as we go. That's actually a better idea. So according to this, I am going negative for 2. So 1, 2. And then I'm going negative in the y-axis for 1, 1. So I'm going to write that on the board. Sorry if this is going to make you guys a little dizzy. So I went negative 2. Now I'm going to go negative 1. So negative 1, right, on our board. Back to our path. Okay, then I'm going to take a right, and I'm going to go I'm going to go more negative. What is this? 1 meter, 2 meter. I'm just going to keep that in my head so I don't have to keep running back to the board. And then I'm going to walk 3 meters to the south, which is our negative y. And then I'm going to call this my endpoint. And my goal here is to look back at my starting point and to be able to tell you the displacement between where we ended and where we started. Now, if you guys have noticed, we've created some little rectangles here. So I'm going to go over the board and I'm going to keep writing this so you guys can see what I'm talking about. Let me zoom out a little bit because that way you can see what I'm writing. I'm going to switch to green because that marker seems to be the darkest. All right, so we started out by going 2 in the negative direction, so I'll write negative 2 here. Then we went down negative 1. Then we went negative 2 in this direction. And then we went down, or south, for 3, negative 3. Now, I'm just showing that the change is, so really I should write something like this. Delta negative 2, or as you were, negative 3, and this should be delta, forget it. I should really just keep track of it this way, right? 2 this way, down this way, 2 more this way, so that would be negative 4, and then down to negative 3, or down negative 3, which is negative 4. All right, so what is our total distance that we traveled? Well, 2, 3, 4, 5, 6, 7, 8. So if I wanted to know distance, I'll write it over here, is 8 meters. Now displacement. That's a little tougher, right? We now have x and y values. So the easiest way to do this is to remember that x and y values can't be added together. X and y distances, you can't add a horizontal to a vertical. If you do, you'll end up with a diagonal, and well, that's what we're trying to get to, but we don't want to do that until we have all our numbers together. So what I'm going to do is I'm going to make a chart, and I'm going to sum all of our x values and all of our y values to figure out how much x and how much y we went. So for x, we went negative 2, and then we went another negative 2. And that's all we did on the x, right? I'm ignoring the y values right now. I'm ignoring these ones right here because I'm just filling out this chart. So negative 2 and another negative 2, okay? And then y values, we went negative 1, and then we went negative 3. So negative 1, negative 3. Now you're probably already noticing that I could have just looked at the final point down here and ignored the whole path. Yeah, remember we talked about that? I could have just looked down here, and this coordinate is actually negative 4, negative 4. Okay, because if I add up these, if I sum them, we get negative 2 and negative 2 is negative 4, and negative 1 and negative 3 is negative 4. We end up at the coordinate negative 4, negative 4. Okay, so we have two pieces of information. We have our starting point now, which is 0, 0, and we have our ending point, which is negative 4, negative 4. So how far did we go in the x direction from where we started? Negative 4. So negative 4 is how we went, is our change in x, and negative 4 happens to be our change in y. Now, we are close, but we don't yet have a single value for the actual distance between here, displacement from here to here. That's the really important information, is how do we get from here to here? And if you look the way I drew that, you probably might have already figured it out. We need to make a triangle out of it. Okay? Pythagorean theorem in physics is usually not called Pythagorean theorem. It's called the distance formula, or it's called the displacement formula. That's what I've always called it. So let's draw a triangle real fast. Our x value is negative 4. Our y value is negative 4. Okay, and we know that if we get this path right here, that is the same as this path right here. Even though I'm drawing it in a different direction, that actually means this path right here, right? We're just getting the magnitude. We're getting the number for how far we went. We'll worry about the direction here in a moment that we're actually facing. And we'll have to do a little bit of trig to do that. So negative 4, negative 4. Okay, now we know the formula. A squared plus b squared equals c squared. Okay, and that if we want to find c, which is the hypotenuse of that triangle, we take the square root of the squares. Square root of a squared plus b squared equals c. And I kind of like to start here. I kind of skip this part most of the time because this formula is very familiar for me. It's the distance formula. Okay, and most of the time this is x squared and y squared, which is what these are. So negative 4 squared plus negative 4 squared is 16 plus 16, which is 32. And we end up with the square root of 32 being the total distance I traveled across our floor from end to end. Okay, now let's simplify that and make it a more reasonable, because to keep the square root, it's right, but it doesn't mean anything to me personally, right? So the square root of 32 is about 5.66 meters. So 5.66 meters. Cool. All right, so we know how far I went. Now, how am I going to figure out in which direction I went? I started here. So if I were to say, and you couldn't see this video right now, I were to say, oh, I started at this location and then I went to this location, you might say, well, which direction did you travel? And that's where we kind of have to do a little trigonometry, right? So let's do that real fast. So what we're going to do is I'm going to go back to our original drawing. I'm going to say that this angle here is what we're looking for. If we can find that angle, or we could even say, let's pick this angle instead, because this is where we started, right? We want to know in which direction we were from where we started. So we might even pick the angle right above it. But it doesn't really matter, because we can go back to our triangle, and we know that if we can find this angle, we know this is a 90-degree angle, that that'll tell us the direction we're going, and then what we can do is we can just invert our answer to being downward. That's easy to do. All right, so how do we do this? How do we find the direction we traveled? Well, we got to use SOHCAHTOA, and I did promise that I would not put that in this video. So if you know how to do it, if you can find the angle that I traveled to go from point A to point B here in my classroom, go ahead and find it. But in the next video, I will describe it in more detail. Anyways, Mr. McLeod out. If you have any more questions about these sorts of things, let me know. And yeah, good luck.